Yo, we are looking at section 2.4 where we are looking at this absolute value function, and we'll be looking at functions and their graphs and seeing what happens to that. We'll be looking at domain and range, and we'll also be looking at inequalities. And if we look at the basic examples of absolute value, it's just a distance from 0. So the distance from 0 to 11 is 11. The distance from 0 to negative 11 is 11. And that is the same concept we're looking for this entire section, but they can be a little more difficult. So sometimes it's nice to think that x values are always going to remain the same, and all of the y values are going to be positive. So if it was positive before, it will remain positive. If it was negative before, just like this example here, it goes to 11. So if we're looking at this graph, all of these x values remain the same. All of these positive y values remain the same. But all of these negative y values will now become positive. So it's going to reflect over the y-axis and look like this. And in the next example, same type of approach. All of these y values are positive, so it will remain the same. All of these negative y values would then become positive and look like this. In the next example, we have all of these positive y values. They will remain the same. All of these negative y values will pivot at the x-axis and reflect and look like this. Here we're looking at range, and I gave lots of different examples of this. So all negative y values become positive, all positive y values remain positive. And so we have this where we have some negative and it goes into positive. So just like this graph from above where we had some going down here, these became positive. And if we looked at this range, it would be from negative, that's our lowest y value, to positive infinity. And that's what's happening with this first example. It pivots here. So whenever we go over the x-axis, this is going to be our range. Here's an example where we have all positives, and we see that the range stays the same. Here we have all negatives, negative infinity to negative 2, and we see that they all become positives, positive 2 to infinity. And here we see, once again, we cross over the x-axis from negative to positive 2, and we still have that same one. So we see all the different types of examples of those types of problems. Here we're looking at the domain and range of the function as well as its absolute value. In both cases, once again, our x values don't change, so our domains don't change. So our domains are negative infinity to infinity for both. Here, my lowest y value was negative 1, and it goes up to positive infinity. Just like the one before, we cross over the x-axis, therefore it pivots, and we get from 0 to infinity. Next up, we're going to do the same thing, except we're looking at a graph. Here we look at our domain. My smallest x value is negative 4. My biggest one is 8. My range, my lowest y value is negative 4. My highest is 8. It is just a coincidence that it is the same. Here, once again, our domains remain the same. We had negative y values and positive, so it pivots. So you see I've drawn in black what happens to what's below. So we would have this kind of a two-peaked mountain. Our lowest y value is 0. Our highest is 8. Here we're looking at interval notation of what's happening around these two graphs, what happens when they equal each other. So these are just the intersection points. So they intersect at the x value of negative 2 and the x value of 2. As you can see, we use braces here. What that means is each one of these numbers included inside is a solution. And so that doesn't mean it goes from negative 2 to 2. Only negative 2 and positive 2 are a solution to that. And this next one is saying where is y sub 1, or the blue graph, less than y2, the red graph. And so this is where it is below. So we see this is where this v is formed below, and this happens from negative 2 to positive 2. And we use parentheses here because it doesn't include those values. So everything between negative 2 and 2, this blue region is below the red region, or y sub 1 is less than y sub 2. And this last one, we're looking at where is the blue y sub 1 greater than or above y sub 2, or the red one. And so this happens from negative infinity to negative 2. And then once we hit there, we go to here where it is equal. And then it goes below, which is where we go here. And then we come back to 2 and on to positive infinity. that graph will be above it. Here we're solving each of these, so it's very similar to the problem that you just looked at, except now instead of looking at a graph, we're solving analytically. And so when looking at this, so in this next problem, we see that we don't have the absolute value isolated with this +3. So our first step is to do what we do over here in black. We add or subtract that 3 from both sides. Now that we have this absolute value isolated, then we can solve as we see here in these three situations. So we have to set this equal to 2 as well as -2. So you can split it up and write 2x plus 1 equals 2 and solve, and then 2x plus 1 equals -2 and solve. I just choose to do it kind of both in one step. So we still subtract 1 on both sides. I get 1 over here. I get -3 here. Then I divide by 2 here. That gives me 1/2 and -3/2. We're using the equal sign, which means we use the braces, because that means that those are the only solutions, -3/2 and 1/2. And here again, same solving that's happening. We've just changed the signs here. So it was less than or equal to. So as you can see, both of these here are less than or equal to. The solving is exactly the same. I get the same numbers. Because it is less than or equal to, that's when I use braces. If this line underneath was gone and it was just less than, then I would be using parentheses here. And this last one, same thing here. We're dividing, we get -3/2, and we get 1/2 once again. We're using braces, or brackets, sorry. And then we have from -infinity to -3/2 union 1/2 to infinity. And this next one, just like the one above, we have to isolate the absolute value. So we add the 9 first. Once we do that, then I use 6 and -6. Then I solve by subtracting 2. I get -8, 7x, and +4. Then I divide by 7, and I get a solution set. So here, once again, I use these braces, but they already have them for you, so you just have to put the numbers. Next problem, once again, we have to isolate the absolute value. So I have to first add the 16, divide by 4. Then, once I get that number, I get 4 here, which means I'm also setting it equal to -4. It's opposite. Now I solve by subtracting 3, I get 1. I subtract 3, I get -7. I'm using braces once again for -7 and 1. For number 11, it's already isolated, so I just have to solve for 14 as well as -14. I solve. The thing that happens differently here is when I am dividing by a negative, that means we have to change our signs from greater than, and they both become less than. And in looking at this, sometimes it's a little unsure of whether or not it's going to be -5/8, comma 23/8 parenthesis. You just pick a number that's in between these two numbers. So I pick 0. Is 0 less than -5/8? No, it is not. Therefore, it must go to the outsides. So I know that every number on the outside of -5/8, from -infinity to -5/8, and everything that's greater than 23/8 is part of my solution. And this next one's a little bit different because we're looking at 0. So when we solve this, we just get 32. But what this means is that 32 is the only number that this will not work for. I plug in 32, I get 4 minus 4, which is 0, and 0 is not greater than 0. So we have to write it in terms of an interval notation where I have -infinity to 32, parenthesis, union, parenthesis, 32 to +infinity. 13 and 14 we don't have to do any work here because absolute values will never be less than a negative number. So this is an empty set. And below here, absolute value will always be greater than or equal to a negative. So this is going to be -infinity to infinity.